In the last lecture, we were discussing conservation equations. I had derived for you the conservation equation in the form of these vector differential operators here. I derived for you the conservation equation in the form of these vector differential operators here, the gradient, the divergence and the Laplacian. And I had expressed these vector differential operators in terms of the scale factors in an orthogonal coordinate system. Okay. So, these were the expressions for the vector differential operators in the in terms of the coordinates x a, x b and x c and the scale factors h a, h b and h c in different orthogonal coordinate systems. These can be used for a general coordinate system which is orthogonal, where the 3 unit vectors are all perpendicular to each other. And then we were looking at the physical meaning of the gradient operator. Okay. These are vector operators in 3-dimensional space, which are extensions of the operators in 1 dimension, the derivative and the integral in 1 dimension. These are the equivalents of those in 3 dimensions. Of course, the equivalents of these in 3 dimensions in, for example, a Cartesian coordinate system are partial c by partial x, partial c by partial y and partial c by partial z. Okay. These are the components in a Cartesian coordinate system, for example. Similarly, you will have components in a spherical or a cylindrical coordinate system for these derivatives. However, the components in a coordinate system depends upon the choice of coordinate system. If I rotate the axis, for example, these 3 components will change. So, they depend upon the coordinate system that is imposed by the observer in order to analyze the field. The vector differential operators, on the other hand, are independent of coordinate systems. Okay. They will have specific values for the components of these operators will have specific values for specific coordinate systems. However, these operators themselves have an identity, a magnitude, or in the case of scalar operators, or a magnitude and direction in the case of vector operators, that are independent of the underlying coordinate system and that are real physical quantities, okay, in space. And we were trying to analyze these for a 3-dimensional coordinate system. So, in this we first looked at the gradient. Okay. If I am at a location x, y, z, okay, and I travel to a nearby location x plus delta x, y plus delta y and z plus delta z. Okay. What is the change in a concentration between these 2 locations? The concentration field, for example, how does it vary as you move from one location to a nearby location? Okay. We had derived this using differentiation, okay, using chain rule as delta x times partial c by partial x plus delta y times partial c by partial y plus delta z times partial c by partial z. Okay. And I had written this as the product of a gradient operator, okay, here, and a change in the coordinate, okay, which is the second line over here, a change in the coordinate, that is the second line here. Okay. I had written this as delta x vector, okay, dotted with grad c. Okay. While expanding out the concentrations, we had expressed the concentration in terms of the x, y, z coordinates. Okay. However, this delta x vector, the displacement between 2 nearby locations, is a vector that is independent of the coordinate system. Okay. If you have 2 nearby locations, the change in the displacement vector from one location to the other, the components of that will change if you change the coordinate system. The vector itself is independent of coordinate system. Similarly, the difference in the concentrations is independent of coordinate system, okay, regardless of what coordinate system you use to analyze the problem. The difference in the concentrations has to be independent of coordinate system, and that implies that this gradient of the concentration that is a vector at a location which is independent of coordinate system. Okay. So, this gradient of the concentration at a given location is a vector which is independent of the coordinate systems. The components of this vector will of course depend upon the coordinate system used, but the vector itself is a real physical entity in 3-dimensional space which is independent of the coordinate system used. And this gradient of the concentration or the gradient of any scalar is something that is uniquely defined at each location in space. Okay. And the physical interpretation of this gradient is that if I go from one location x to a nearby location x plus delta x, the difference in concentration between these two locations is the dot product of the displacement delta x dotted with the gradient of the concentration, okay, where the gradient of the concentration is uniquely specified at each point in space. Okay. Dot product is the magnitude of the two gradient of the displacement and the gradient of concentration times cosine of the angle between the two. So, when the two are collinear, that is when you are traveling along the direction of the gradient, that is when the difference in concentration is a maximum. Okay. That means that the gradient of the concentration is in the direction of maximum variation of concentration, okay, of maximum increase of concentration. Okay. Whereas, the opposite direction to the gradient is the direction of maximum decrease of concentration. Also, if the angle between these two is pi by 2, okay, or cos theta is equal to 0, which means that the displacement vector delta x and the gradient of concentration grad c are perpendicular to each other, then there is no variation in the concentration, okay, because cos theta is equal to 0. That means that the gradient of the concentration is perpendicular to surface of constant concentration. Okay. So, if there is a surface around this point along which if you move in any direction the concentration does not change, the gradient vector is perpendicular to that surface. So, the gradient vector at a given location picks out the direction of maximum variation in the concentration, and it is perpendicular to the direction to the surface of constant concentration. Okay. Now, so that is the gradient vector, it gives you the variation about a point. Okay. So, that is the differential, okay, part, okay, of the definition. What is the integral relation that relates the gradient? Okay, that is equivalent to the integral, okay, between 2 points of the derivative. Okay, how is that related to the difference in the derivative at the endpoints? In one dimension, of course, there is only one direction we can travel in, but in 3-dimensional space there are multiple directions that we can take to go from one point to the other. Okay. So, the integral theorem for the gradient basically states that if I have a 3-dimensional space, and I have 2 points A and B, okay, in this 2-dimensional space, okay, and I travel along this A to B, okay, and the differential displacement, okay, the differential displacement along this path, okay, is dx, okay, the differential displacement along this path is dx. Then the integral relation is that integral, okay, between A and B, okay, of dx dotted with grad c, okay, is equal to the concentration at the location B minus the concentration at the location A. Okay. That is the relation for the integral relation for the gradient. Okay. To prove this, you can convert this integral into the sum of a large number of differential displacements. Okay. So, I can write this as sum I is equal to 1 to n, okay, delta x vector dotted with grad c at delta x I dotted with grad c at the location x is equal to x I. Okay. So, what you do is you separate out this path into a large number of differential displacements. Okay. So, the first one will be delta x 1, the second one will be delta x 2, the last one will be delta x n minus 1, and then finally I will get to the location B. Okay. So, divide into a large number of differential displacements. Okay. So, let me write the endpoints here. Okay. So, okay, so the first differential displacement goes from A to x 1, okay. The second one goes from x 1 to x 2, okay. The third one from x 2 to x 3, okay, etcetera, up to x n minus 1 and then to x b. Okay. These are vectors which go from the initial location to the final location, all of these delta x i's. Okay. Okay. Now, we know that from the definition of the gradient, okay, from the definition of the gradient here, okay, for a differential displacement, okay, from the definition of the gradient here for a differential displacement, we know that grad delta x 1 dot grad c at x 1 is equal to c at x 1 minus c a. Okay. So, the first displacement if I take, it goes from x a the first differential displacement goes from x a to x 1, okay, and that is delta x 1. So, if I take delta x 1 dotted with the gradient at that location, I get the difference between the two endpoints c at x 1 minus c at x a. Okay. Similarly, if I take delta x 2 dotted with grad c at x 2, okay, will be equal to c at x 2 minus c at x 1. And so on, I can do this. Okay. Finally, I will get delta x n minus 1 dot grad c at x n minus 1. Okay. Is equal to c at x b minus c at x n minus 1. Okay. That is for this last one here. Okay, that is for this last one here. And the left side of the equation is the summation of all of these. Okay, it's the summation of all of these. Okay, all of these differential displacements dotted with the local gradient at that location. Okay, the sum of all of these is the left side. On the right side, you can see that here, for example, x 1 c at x 1 cancels. Like that, you will get cancellation of all terms between internal points, okay, until this term will also cancel out, and the summation the summation will just give me c at x b minus c at x a. Okay. Okay. And in the limit as delta x goes to 0, this is just integral, okay, dx dot grad c between a and b. Okay. Okay. So, that is the integral theorem, okay, for the gradient. Okay. the integral of the gradient of a concentration along a path between two locations is equal to the difference in the concentration at the two endpoints. Okay. So, that is the it appears very similar to what we had in one dimension. Okay. It appears very similar to what we had in one dimension. Integral of the derivative is the difference in the value at the endpoints. Okay. However, there is an important difference. Okay. Between 2 points A and B, there are multiple paths that one can take. Okay. You can take a path like this, you can take a path like that, and so on. There are multiple paths that one can take between A and B. What this integral relation tells you is that the integral of dx dot grad c along all of those paths has to be exactly the same, because it is equal to, it depends only upon the endpoints. It does not depend upon the specific path taken. Okay. So, therefore, the integral theorem for the gradient, which tells us that the difference in concentration between two endpoints is the integral of the differential displacement dotted with grad c, that is independent of path and it depends only upon the endpoints. Okay. So, that is a more powerful relation than in just one dimension, where there is only one way you can get from A to B. So, one corollary is what I had already told you, the integral of the dx dotted with grad c is the same along any path between A and B. The second corollary is that if I go in a closed path, I start at the location A and come back to the same location A, the difference in concentration is 0. Therefore, the integral of the displacement dotted with the gradient of C over any closed path has to be equal to 0. Okay. So, that is the second corollary. Okay. So, that is the physical meaning of gradient and the integral theorem of gradient. Gradient of the concentration is a vector at each location, the gradient of a scalar, okay. A vector at each location which gives you the direction of maximum variation of that scalar, perpendicular to surfaces of constant value of that scalar. Okay. And it is uniquely specified at each point in space, a vector that is uniquely specified at each point in space. And the integral theorem is that the integral of the differential displacement dotted with the gradient of the scalar is equal to the difference in the value at the two endpoints. Okay. Let us now look at the second differential operator, divergence. Okay. In a Cartesian coordinate system, you recall that the divergence of J was written as partial J x by partial x plus J y by partial y. In order to understand the physical meaning of this, let us step back a little and recall how we had derived the conservation equation. Okay. The conservation equation, you recall, was that partial C by partial T plus del dot C V is equal to minus del dot J plus S. Okay. That was the conservation equation. How did we derive it? X, Y, Z. I had taken a differential volume, okay. Okay, and calculated the flux in, okay, the flux in, okay, and the fluxes out. Okay. I calculated the fluxes in and I calculated the fluxes out. So, I had taken, okay, the summation of the flux, okay, okay, J x at x minus delta x by 2 times the surface area delta y delta z. Okay. Those were the fluxes in at the location x minus delta x by 2. Okay. those were the fluxes that were directed inward. Okay. And then the fluxes outward were at the locations j x at x plus delta x by 2, delta y delta z plus j y at y plus delta y by 2, delta x delta z plus j z at z plus delta z by 2, delta x delta y. I had taken that summation and then I had divided throughout by the total volume. Okay. So, at the location, at the left location for example, the flux is inward in the plus z direction. Okay. It is inward. Okay. If I take the unit vector, the outward unit vector in the minus E y direction at this location. Okay. At this location, the outward unit vector is in the minus E y direction. That means that j y is equal to minus n dot j. Okay. 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 So, this at y minus delta y by 2 is equal to minus n dot j at y minus delta y by 2. Okay. Okay. Similarly, for x and z. Okay. Similarly, for x and z, the outward flux at the location y plus delta y by 2. Okay. At that location, the outward unit normal is in the plus y direction. Okay. At that location, the outward unit normal is in the plus y direction. Therefore, j y at y plus delta y by 2 is in the plus y direction. So, I have to take the dot product of the outward unit normal and the flux vector. Okay. So, you can see that on the three faces at x minus delta x by 2, y minus delta y by 2 and z minus delta z by 2, the fluxes are inward. So, that is equal to minus n dotted with j. On the other three faces where the flux is directed outward, it is equal to plus n dot j. Okay. Therefore, this entire summation can be written as summation of delta S I times minus n dot j at x I, where x I is the location of the center of the surface and delta S I is the surface area. Okay. So, this is equivalent to the summation that I have here, because the unit normal on the left, the bottom and the rear surfaces are in the minus E x, E y, E z directions. Those on the front, the top and the right surfaces are in the plus E x, E y, E z direction. Therefore, I can uniformly write this as minus n dot j times the surface area on each of those 6 surfaces. Okay. So, I calculated the sum of these and then divided by the total volume delta V. Okay. This is equal to minus del dot j, which was this term on the right side. Therefore, I can define the divergence. I can define the divergence. Is equal to summation over delta S I into n dot j by delta V is equal to limit as delta V goes to 0 of the summation. This is for a regular cubic surface where I have 6 surfaces which are planes. If I had this definition can be extended to any general surface. The surface V, so differential surface delta V with surface S, okay, okay, and outward unit normal n, okay, and outward unit normal n, and I have some field, okay, let us say the vector field, okay, let us say the flux or the velocity or some vector. Okay. Then I can define the divergence of this vector field as integral over the surface, okay, of n dot A divided by delta V in the limit as delta V goes to 0. Okay. This is the definition of the divergence. Okay. This is the definition of the divergence, okay, or del dot J as the case may be at a point. Okay. So, this divergence is a scalar for a vector field, whether it is the velocity v or the flux j, the divergence is a scalar, okay, at a location which is uniquely specified. How do I find out the divergence? I go to that location, construct a small differential volume around that location delta V with surface S, and that surface has outward unit normal n. You take the integral over the entire surface of n dotted with that vector, which in this case is j, okay, n dotted with j, okay, integrated over the entire surface divided by delta V in the limit as delta V goes to 0. This term, okay, will be independent of the volume or its shape. Okay, it will be independent of the volume or its shape. It will depend only upon location. It will be specified uniquely at each location in space. So, by this construction you can find out what is the divergence at a location, and it is that same construction that we had used to get this del dot j term here. Okay. We had taken the surface, dotted the flux with the outward unit normal, the negative of that divided by volume in the limit as that volume goes to 0, you get this divergence of the flux. Okay. So, that is the definition of the vector divergence. The divergence of a vector gives you a scalar, okay, and it is uniquely specified at each point in space, okay, and it is obtained by constructing a small differential volume independent of the shape of that volume. You will get a unique value for the divergence at a particular location. Okay. Okay, what is the physical meaning of divergence? Okay, so, the physical meaning of divergence and the integral theorem for divergence I will discuss in the next lecture. Okay. Just as we had an integral theorem for integral relation for the gradient, we can also derive an integral relation for the divergence. How do we derive that integral relation and what does it physically mean? Those things I will discuss in the next lecture. I will see you then.